Just say it, man. Don't make me ask 20 questions.
What is the point?
Get to the point.
Just say it already!
Welcome to the Podgram. Get you some nerd stuff from Geoffrey Hinton, the Godfather of AI.
What was the moment that you realized AI development is moving faster than our means to contain it?
I guess in early 2023, it was a conjunction of two things. One was ChatGPT, which was very impressive. And the other was work I've been doing at Google on thinking about ways of doing analog computation to save on power, and realizing that digital computation was just better. And it was just better because you could make multiple copies of the same model. Each copy could have different experiences, and they could share what they learned by averaging their weights or averaging their weight gradients. And that's something you can't do in an analog system.
Is there anything about our brain that has an advantage because it's analog?
The power. It's much lower power. We run at like 30 watts. And the ability to pack in a lot of connections. We've got about 100 trillion connections. The biggest models have about 1 trillion. So we're still almost 100 times bigger than the biggest models. And we run at 30 watts.
Is there something about scaling that is a disadvantage? So you said it's better, but just as quickly as something nourishing or positive can spread, so can something that's a virus or something deleterious can be replicated quickly. So we say that that's better because you can make copies of it quicker.
If you have multiple copies of it, they can all share their experiences very efficiently. So the reason GPT-4 can know so much is you have multiple copies running on different pieces of hardware. And by averaging the weight gradients, they could share what each copy learned. You didn't have to have one copy experience the whole internet. That could be carved up among many copies. We can't do that because we can't share efficiently.
Scott Aronson actually has a question about this. Dr. Hinton, I'd be very curious to hear you expand on your ideas of building AIs that run on unclonable analog hardware so that they can't copy themselves all over the internet.
Well, that's what we're like. If I want to get knowledge from my head to your head, I produce a string of words and you change the connection strengths in your head so that you might have said the same string of words. And that's a very inefficient way of sharing knowledge. A sentence only has about 100 bits. So we can only share about 100 bits per sentence, whereas these big models can share trillions of bits. So the problem with this kind of analog hardware is it can't share. But an advantage, I guess, if you're worried about safety, is it can't copy itself easily.
What does it mean to understand?
Okay. That's a question I'm happy to answer. So, again, I think most people have a wrong model of what understanding is. If you look at these large language models, there's many people, particularly people who from the Chomsky School of Linguistics, who say they don't really understand what they're saying. They just are using statistical correlations to predict the next word. If you look at the first models like that, I think I probably made the very first language model that used backpropagation to train the weights to predict the next word. So you backpropagate the error in predicting the next word. And the point of the model was to show how you could learn meanings for words, or to put it another way, to show how you could take a string of words and learn to convert the words into feature vectors and interactions between feature vectors. And that's what understanding is. Understanding a string of words is converting the words into feature vectors, so that you can use interactions between features to do things like predict the next word, but also to do other things. So you have a sentence which is a string of symbols. Let's not talk about word fragments. I know these transformers use word fragments, but let's suppose they used whole words. It's easier to talk about.
Right.
And it would just make them work a bit worse, that's all. They'd still work.
Sure.
So I give you a string of words, some text. The meaning isn't in the text. What you do is you convert those words into feature vectors, and you've learned how feature vectors in context, how the features should interact with each other to do things like disambiguate the meanings of ambiguous words. And once you've associated features with those words, that is understanding. That's what understanding is. And that's what understanding is both in a large language model and in a person. In that sense, we understand in the same basic way they understand. It's not that when we understand, there's some magical internal stuff called understanding. I'm always trying to get rid of magical internal stuff in order to explain how things work. We're able, using our big neural networks, to associate features with these symbols in such a way that the features all fit together nicely. So here's an analogy I quite like. If you want to model 3D shapes, and you're not too worried about getting the surface just right, you can use Lego blocks. Suppose they're big shapes, like a car. You can make something the same shape as a Porsche with Lego blocks. The surface won't be right, but it'll have the same space occupancy.
Sure.
So Lego blocks are a kind of universal way of modeling 3D structures. And you don't need many different kinds of Lego block. Now, think of words as like Lego blocks, except that there's a whole bunch of different Lego blocks with different names. What's more, each Lego block has some flexibility to it. It's not a rigid shape like a piece of Lego. It can change in various directions. It's not completely free. The name tells you something about how it can change.
Okay.
But there's some flexibility to it. And sometimes there'll be a name and it's two completely different shapes it can have. But it can't have any old shape. So what we've invented is a system for modeling much more complicated things than the 3D distribution of matter, which uses high-dimensional Lego blocks. So the Lego blocks with, say, 1,000 dimensions. And if you're a mathematician, you know 1,000-dimensional spaces are very weird things. And they have some flexibility. And I give you the names of some of these Lego blocks, and each of which is this 1,000-dimensional underlying.
Sure.
And they all deform to fit together nicely. And that's understanding. So that explains how you can learn the meaning of a word from one sentence without any definitions. So if, for example, I say, she scrommed him with the frying pan, you have a sense of what scrommed means. It's partly phonetic, but because the ed on the end tells you it's a verb. But you think it probably means she hit him over the head with it or something like that. It could mean something different. She could have impressed him with it. You know, she cooked such good omelettes that really impressed him. It could mean she impressed him. But probably it means she hit him over the head or something like that, something aggressive like that. And you get that from just one sentence. And nobody's telling you this is a definition of scrommed. It's just that all the other Lego blocks for the other words, she and him, and all those other words, adopt shapes that fit together nicely, leaving a hole. And that hole is the shape you need for scrommed. So now that's giving you the shape that scrommed should be. So that's how I think of language. It's a modeling system we've invented where there's some flexibility in each of these blocks. I give you a bunch of blocks and you have to figure out how to fit them together. But because they all have names, I can tell other people about what my model is. I can give them the names. And if they share enough knowledge with me, they can then figure out how they all fit together.
So are you suggesting help the audience understand what understanding?
I think what's going on in our heads, and that's what's going on in these large language models. So they work the same as us. And that means that they really do understand.
One of Chomsky's counter-arguments to that the language models work the same is that we have sparse input for our understanding. We don't have to feed the internet to ourselves. So what do you say to that?
It's true that the language models are trained on much more data. They are less statistically efficient than us. However, when children learn language, they don't just learn it by listening to the radio. They learn it by being in the real world and interacting with things in the world. And you need far less input if you train a multimodal model. It doesn't need as much language. And the more If you give it a robot arm and a camera and it's interacting with the world, it needs a lot less language. So that's one argument. It still probably needs more than a person. The other argument goes like this. The backpropagation training algorithm is really good at packing a lot of knowledge into a few weights, where a few is a trillion, if you give it a lot of experience. So it's good at taking this huge amount of experience, sucking the knowledge out and packing it into a relatively small number of weights like a trillion. That's not the problem we have. We have the opposite problem. We've got a huge number of weights, like 100 trillion, but we only live for 2 billion seconds. And so we don't have much experience. So we need to be optimized for making the best use you can of the very limited amount of experience you get. Which says we're probably not using backpropagation. We're probably using some other learning algorithm. And in that sense, Chomsky may be right that we learn based on less knowledge. But what we learn is how to associate features with words and how these features should interact. I still believe that fast weights are going to be very important. So synapses in the brain adapt at many different timescales. We don't use that in most of the AI models. And the reason we don't use it is because you want to have many different training cases that use exactly the same weights. And that's so you can do matrix-matrix multiplies, which are efficient. If you have weights that adapt rapidly, then for each training case, you'll have different weights because they'll have rapidly adapted. So what I believe it is a kind of overlay of fast weights on slow weights. The slow weights are adapting as per usual, but on top of that, there's fast weights which are adapting rapidly. As soon as you do that, you get all sorts of nice extra properties, but it becomes less efficient on our current computers. It would be fine if we were running things on analog computers. So I think eventually we're going to have to use fast weights because they lead to all sorts of nice properties. But that's currently a big difference between brains and the hardware we have. One thing I think I do is this. Look for a place where you think everybody's doing it wrong. You just have an intuition everybody's doing it wrong. And see if you can figure out how to do it better. And normally what you'll discover is eventually you discover why people are doing it the way they're doing it, and that your method that you thought was going to be better isn't better. But just occasionally, like if you think everybody's trying to use logic to understand intelligence, and we should be using neural networks, and the core problem of understanding intelligence is how the connection strengths in a neural network adapt, just occasionally you'll turn out to be right. And until you can see why your intuition is wrong and the standard way of doing it is right, stick with your intuition. That's the way you'll do radically new things.
Thanks for listening to this installment of The Podcram. I hope it contains something useful for you. If you enjoy these selections and are curious about the curator's own thoughts, you can check out my other podcast, Psychic Lube, where I share concise concepts meant to grease the intellectual gears and help get your creative juices flowing. Each episode is an ongoing collaborative project that welcomes listeners to expand or rebut its points by email or comment, the most interesting of which get incorporated through periodic re-recordings. As always, if you're intrigued by today's content, I encourage you to go listen to the full podcast in its original form directly from its creators so that their sponsors keep paying them to make stuff for us and nobody feels compelled to sue me for copyright infringement. Now, get off your phone and go do smart stuff. Have a productive day.